Hi, welcome to question 2. So this is a question on binary trees, specifically complete binary tree. So a complete binary tree kind of is what it sounds like. Every level is filled except possibly the last part. So we basically fill this binary tree from left to right as much as possible before we get to the last level, in which case you can have nodes with one child or leaves. Or actually no nodes at all. So basically the previous level would be leaves. Okay, and then the problem is a pretty interesting one. So we want to basically implement these dashed pointers, which represent next pointers for each node. And so what these dash pointers are doing, they're basically linking the nodes in level order, right? So we're going from 0 to 1 and 2 to 3, 4, 5, 6, and then to 7, 8, 9. If this reminds you of a graph, basically maybe a tree traversal algorithm, it's probably a breadth first search, because remember in breadth first search we complete one level before we go to the next level and so on and so forth. So same idea here, except that now we're working with tree nodes. So we have a class called bin tree that is similar to a normal binary tree with left and right pointers, except that it also has an extra pointer called next that is supposed to point to the next bin tree node in the tree in level order. And our job is to fill in the Lincoln level order method on the next page to fulfill its comments. Okay, so again, let's just read the comment just to make sure that we really understand what's going on. So we want to link the tree rooted at root in level order by destructively modifying its .next pointers. Remember, destructively modifying means that we mutate the tree in place. This tree must be a complete binary tree with its next pointers initially null. So basically our job is to set all of these next pointers so that our tree accomplishes something like this. Okay, oops, sorry. That was me toying around with code. Okay, so there are many different implementations for this method. I would say that you could probably implement one on your own before you watch this video and actually test it out. In IntelliJ, you could substitute an actual implemented binary tree class instead of bin tree and just replace that. And then, write a test maybe, inside a main method, just create a binary tree like this one, and then it would also be helpful to have a print function just so that you can actually see how the nodes are being laid out. But again, it's up to you how much you want to go into testing. But in this case, I'm just going to be writing something that represents one specific implementation. Again, you can have many different ways of writing this. Okay, so one thing that I want to start off with before we jump into code, and it's really important that you conceptually think about how you would approach this, deviating away from programming. So one thing that I'm noticing is that the pattern here is kind of simple in a sense. So basically, whenever you reach the last node on a level, your job is to check if it has any nodes in the next level, right? So if there are any nodes in the next level, when you're at the last node in the previous level, and your job is to set the next pointer of that previous level node to the first node on the next level, right? So somehow, in order to implement all of these types of pointers, we need to keep track of what the basically of what the next nodes are, right? Okay, so that is one thing that I'm thinking about. Another thing is if you look at what's happening inside the tree instead of like on the outer edges, you notice that it's kind of impossible, right, to set the next pointer of 1 when you're actually at the node 1, right? Because there's really no way that you can access a sibling of a node unless you're the parent, because the parent can actually oversee all of its children, and so they can manipulate the next pointers of all of its children. So actually, if you wanted to set the next pointer of node 1, you would have to do that at the parent of 1 and 2. So that's one thing. So you kind of have to think one step ahead. Okay, so let's also about the previous thing, about the previous point where you keep on changing, basically you have to implement this cross-level pointers. You might want to keep a variable that would update itself based on which level you're going to next, right? So that variable could keep track of the node, maybe that the first node in a row, and then that variable could update itself whenever you have to move to a next row. Okay, so with those things in mind, let's actually start implementing this. I'm going to clear that. Okay, so I'm going to do this iteratively. You can basically do it recursively also, because everything iterative can also be written recursively, but I think better iteratively, I guess, so I'm just going to do an iteration. So I know that I'm going to need a for loop. You can also do a while loop, but I'm just going to do a for loop because it kind of keeps all the things I need in one line. So bin tree node is going to have to equal something. I don't know what yet. And then my termination condition is going to be as long as the node is not equal to null, right? That's a very standard termination condition. And then at each iteration, I'm basically going to move it to its next node. So I'm going to do something like that. And again, I don't really have anything implemented so far. So this is just me kind of blind guessing what I'm about to do. And so inside this for loop, what I want to do is basically implement all these next pointers. So again, I need to think about the case where we need to implement the next pointers of the children, okay? For example, like in this case, right? If we're at node 1, we need to make sure that we set the next pointer of 3 to point to 4, because at the point where we were at 3, we're not going to have a way to access its sibling, right? So we have to do it one step ahead. So that means that first I need to make sure that the node is actually a parent. So let me just say, if node.left is not equal to null and node.right is not equal to null, then I want to set its node.left.next. Whoops, I don't like how it's always capitalizing things, to be node.right. So that's basically linking the sibling children, right? Okay. Okay, so that's one thing. And now what happens when I move on to node.next? Node.next is actually null, right? Because remember that every next pointer is initially null. So what if I'm basically at the end of my current level? Okay, so that's another case I need to account for, right? So if node.next is equal to null, that means that I need to implement this type of pointer, right? So basically I'm dividing my code into two if cases. The first if case is dealing with these types of pointers. That's the first if case. And then the second if case is dealing with this type of pointer. That's the second if case. Okay, and really that's really all the two types of pointers that I need to care about, right? That's the only thing you see in this diagram. So that's how I'm structuring my code right now. And so let me just comment things. This is for implementing sibling children pointers. And then this is for implementing, that's redundant. This is for cross-level pointers. Okay, so if node.next is null, basically I need to set it to the first node on the next level, right? And then I need to update this first node. And then I need to update, because remember that I was going to keep a variable, right? So here, this is like a variable, for the first node on maybe, let's say, current level, okay? And so I need to basically, to get the first node on the next level, that's basically equal to first node on the current level dot left, right? And then I can update this variable here, update variable for first node on current level. Okay, so that is my like pseudocode. I think writing pseudocode first really helps. Let me actually implement this. So it's going to be a bin tree. Bin tree, I'm just going to say first is going to equal, well, it's going to equal root in the beginning, right? Because we're starting at the very top. And then bin tree node is actually going to be first. Because we want to start from the first node on the current level, right? We do all of the pointer changing, starting from the first node on the current level, go all the way to the very end, to the last node on the current level, and then repeat the whole process. We update the first to be now the 3. We go through this entire level until we get to the last node. Then we re-update the 3, the first node, to be 7, and then go through the entire level until we reach the end of our tree. So hopefully that made sense. That is basically how I'm structuring my code. Okay. All right, so yeah, now I can try to implement this part. So node.next is going to equal first.left, and then I want to update first to be node.next, right? Okay. Or you could also say first equals first.left, but I already assigned node.next to be that, so I'm just reusing what I assigned. And then, okay, so that's good for cross-level pointers. That's basically everything you need. However, for sibling children pointers, we haven't exactly taken care of the part where we update the .next pointer for the right child. So we did it for the left child, right? We did node.left.next equals node.right. We also want to make sure that we do it for the right child, because this updating of the right child's next pointer is going to be what helps us iterate through our for loop, right? Okay, so as long as there is, okay, so basically, in this case, right, we're basically connecting the right child's next pointer to the left child of the next parent. So as long as node.next is not equal to null, right, and node.next means it's looking at, so right now I'm at node 1, and node.next is going to give me 2. Okay, so as long as I have something here, right, then I want to access its node.next.left, and I want to assign that to my node.right.next. And then let's see, is there anything else I need to add? Let me see if I can actually, okay. Okay, so let's see what we did so far, right? So basically we created a variable for keeping track of the first node on the current level. And then we iterated through all the nodes in one level, right? And then basically at the end of that level, we update the first. And so now we start a whole new batch of iterations for the next level. And so as long as node is not equal to null, we're going to be moving node to node.next, okay? And then if